Okay, so we'll start with the second lecture in the series of scientific seminars here at the Faculty of Sciences. And today's lecture will be dealt by the Dominik Kriegner from Institute of Physics of Academy of Sciences of Czech Republic. And it will be about the role of symmetries shaping the magnetic materials for spintronics. And he is a physicist, of course, and he come from Linz originally, where he was doing the it will come up, hopefully. Then he moved from the Linz University to Prague, and from Prague he went for postdoc to Dresden, to Max Planck, and from Technische Universität. And now, since 2022, he's again in Prague, and this time at Institute of Physics of the Academy of Sciences. And in order not to have the blanked screen again, I think you should start.
Perfect.
Thank you.
Okay, so I know I have to go a certain speed so that I'm not again falling back to the black screen. So thanks for the introduction. So as was said, my name is Dominik Kriegner. I now work at the Czech Academy of Sciences Institute of Physics in Prague. And what I will tell you today about is sort of, I try to bring you to a point where I can really show you what we published 2 weeks ago, basically. Yeah? So I try to kind of bring you up to speed on sort of condensed matter physics in the next like 40 minutes or so. All this is, of course, the result of a large collaboration, and some of the names of the people contributing are on the bottom here. In principle, those people are sort of spread around the world. We have collaborators, of course, from Czech Republic, from Austria, where I did my studies, University of Dresden, where I've been for some time, places in Germany, also Mainz, and also in South America, Switzerland. And the last logo, I assume you know from Prague, Charles University. I just summarize here once more sort of how I got to here today, let's say. So I studied technical physics at the Johannes Kepler University in Linz in Austria. So that would be that pin there. There I did all my, kind of at that time it was not yet master and bachelor program, but the diploma studies and the PhD studies. And I worked a lot on structural characterization of condensed matter, let's say by X-ray diffraction and neutron diffraction. This brought me a lot to Grenoble and to Hamburg, where they have synchrotron light facilities which we used for our experiments. After that, I moved to Prague. There was an expert in the field of diffraction, which kind of attracted me to go there. And I worked on Charles University, and I also sort of converted slowly towards the field of spintronics, which I will talk about today. And after sort of 4 years in Prague, I moved to Dresden. I was at the Max Planck Institute for Chemical Physics of Solids. Unfortunately, I didn't pick up a lot of chemistry, I think, because it would help me a lot sometimes in my work, but maybe I can still also learn something today. I started to do thin film growth, so I again changed a bit my sort of kind of work topic. And then I just switched to the TU Dresden, where I really did only spintronics, and now I came back to Prague 2 years ago, and I try to combine these two things at the Institute of Physics. Basically, we try to do growth of thin films for spintronics applications, and that's what I will gonna talk about today. When I'm not in the lab, I have also two kids, so I'm not bored outside of work as well. And of course, we try to go when the weather allows, and also outside. So here's a small sort of outline of my talk. I think a lot of the time we will spend on this introduction, and I will try to sort of really show you some slides which I would show on an international conference otherwise. And maybe it would be also interesting for me to know sort of how much time we should spend on introduction. So maybe with a show of hands, you could sort of indicate how many of you know, at least roughly, what the spin property of an electron is. Okay, at least half. Who does not know? Somebody wants to? Nobody does not know. Very good. Good. So I will give a very brief introduction. I think it's not necessary to understand all the details, but I think a lot of my introduction I will spend on explaining symmetries in crystals, which I think is something very basic graphic, which you will be able to catch from the slides, hopefully. But so why do we talk about all of this? I think the motivation of our work is basically that the present day electronics are sort of on its limits. Nowadays, as you might know, in all the sort of microelectronics, we use semiconductor transistors, and they came a very far way from when they were sort of developed in the 40s, late 40s, where they were like centimeter-sized weird objects, let's say, to what they are nowadays, when you have, every one of you will have billions of those in your pocket, basically. They are now only nanometer-sized, and even Intel is now speaking of the angstrom era, so they are even shrinking things even more. But this shrinking, of course, comes to its sort of physical limits. At some point, you are at the level of one atom, and you cannot shrink down these devices anymore. So we need sort of new concepts, new materials, and that's where our research sort of comes in. We try to find these limits. What are the problems of semiconductors? There are a few of them. Sort of, we have the problem that when you turn off the electricity, that all the information is basically lost, because the information is basically volatile in these chips. And also the speed is sort of on the limit in this gigahertz range where the nowadays processors are working. For the sort of volatility, there are sort of ferromagnetic storage systems which kind of overcome that, but they have also certain problems, because they are also we cannot make them faster anymore, and we cannot make the kind of bit size smaller anymore. This means also the storage density is somehow limited. So clearly we would like to find materials which can be faster. In the ideal case, we would like to come from gigahertz range to the terahertz regime, so 1,000 times faster. And we would like to get rid of this minimization problem, so that we can put things as close as possible together. And for this purpose, actually, we are trying to explore this property of spin of the electron. So the spin is a sort of an intrinsic form of an angular momentum of the electron. So you can sort of live with the picture that it's sort of like an electron spinning left or right. It's not quantum mechanically true, of course, but I think for the purpose of today, that's perfectly fine. And quantum mechanics tells us that these electrons, they can only have two quantized states. This can be spin up, spin down. And for the purpose of today, I think we can simplify this basically by a red arrow pointing up being spin up, and the blue one down, or vice versa, for the second state. So why were we interested in this spin? We are trying to do spintronics, and spintronics is the abbreviation for spin electronics. So we try to exploit this property of spin in addition to the charge. I didn't highlight that, but of course the electron has a charge, and that's what we nowadays use in all the microelectronics as the basic property of the electron. This charge is moving, and by moving charges or charging charges being stored somewhere, we can represent zeros and ones. And we would like to move further and use, in addition, this property of spin, spin up, spin down. And you will see why. So there is already a few devices actually which are sort of commercially available, which use these spintronics properties, and the most successful one, which maybe is already fading out nowadays, are actually the hard disk, the conventional hard disk read heads, which is basically this small tip at the front here, which is hovering over this ferromagnetic storage medium, which tries to read out the bit information below. And that's basically a spintronics device, which uses a multi-layer of this magnetic material, and you can kind of have a low resistance for electric current, which is flowing vertical when these two magnetic moments, which is basically like spins, are aligned parallel versus when they are aligned anti-parallel. And this difference of the electrical resistance is used to basically detect if below you have a 0 or 1 stored in your hard disk. Another sort of already commercially available but not yet very widely used kind of form of a spintronics device is a magnetic random access memory. There are different device concepts. I don't want to go to the detail here, but you can already buy those in form of a chip nowadays, but the storage density is not yet sort of competitive to the other storage technologies. But the advantage is clear, because like now you have a magnetic storage, so it's not like these dynamic random access memories which you typically now have in phones and computers. Again, when the battery is off, information is lost. In the magnetic one, the information can stay because we have a magnetic moment which also stays there. We have spin. The spin property of up and down is still there also when the power supply is off. So the promise basically is that by using these spintronics devices, we are able to kind of save energy because we have a non-volatile storage of information and don't need to constantly rewrite the data information. So why is this actually a problem? We have electronics all around us. Everyone has a smartphone, everyone has sort of some smart devices, home, data centers which we use via AI or Google search or whatever, are using a lot of electricity. And in fact, this is really scary, sort of, that nowadays, from the total kind of electricity production of all of mankind, we are using already to 7 to 8% for all these information technologies. And this is predicted to massively rise in the future, at some point most likely to an unsustainable level. And so we are clearly needing sort of technical solutions to circumvent this problem. So we will in the future further rely on information technologies, but we need sort of devices which maybe consume less energy. And that's basically where the spintronics promise would be, that by these non-volatile memories, we can have lower energy consumption. I would like to sort of go more into this and explain you on the microscopic level a bit sort of what the idea can be. So in addition to this non-volatile storage, there's one sort of thing which currently I think there's no device purely based on that, but I mean, people are still thinking about ideas how to implement that. And currently, I said, sort of, we always use the charge current. So we move charges, and whenever we move charges, we dissipate energy. And now, spintronics, in principle, we could also operate devices where we don't move charges. And there's currently no devices like that existing, but you could imagine that a pure spin current is one where, when you imagine now your electrons, so here we had electrons with spin. Of course, they always have this property of spin, but in current nowadays electronics, we ignore the property of the spin. So that's why we only look at charge current, and in fact the spin current is zero, because all the electrons we move, they are like randomly polarized, half of them up, half of them down. However, now imagine we do it in a more clever way. We move all of those which are having the arrow up to the right, and all of them which have it down to the left. This means effectively we are not moving any electron, because half of them are moving right, half of them are moving left, so no charge current, so theoretically no dissipation, and still we transport spin current, because effectively it would be like 4 electrons with spin up moving to the right. And that would be the most clever thing to do, because then we could really have sort of an information technology device without the kind of necessity to have dissipation in the system. But we need to still think sort of how to do that. And that means basically we need materials which can have these charge currents. And that's where I want to aim at today. We want to find those materials. And for that purpose, I want to kind of maybe reintroduce to you the symmetries, and in particular how the symmetry operations work in crystals. So how many of you actually know about sort of symmetries? And again, sort of like half, the same half like before. Very good. I will go very slow. So I will just introduce you to sort of the basic symmetry operations. Here, for example, a mirror operation. So a mirror operation typically we denote by this sort of fancy M. It's a plane around which we can mirror an object, like the name says. So for this pentagon, it moves from the left to the right by the mirror operation. Now, of course, in the I will come later on the fact how objects are invariant with respect to such symmetry operations or not. But this is just trying to show you how these basic operations work. So the mirror operation is one of them. The next one I want to introduce is a rotation axis, which here you see that for the pentagon, when we have a rotation axis in the center, we can rotate 72 degrees, so 360 divided by 5, and we end up with the same object. So we identify here that there's a 5-fold rotation axis in this pentagon, which is located in the center, and we denote that by basically C5 or Cn in the general case of an n-fold rotation axis. And then we have inversion centers, and inversion centers are points in space around which we sort of invert all the coordinates. So every point here sort of is transmitted to the other side of this point, and by that we transform this pentagon to this one. And now when we will try to understand these symmetries in crystals, but I would first start with some more easy objects. Let's say, for example, this kind of pictogram of a sun or something similar, star. And basically here you need to learn how to look at these things and identify the relevant symmetries. And if I'm not wrong, I mean, you might correct me, I see here that there should be 8 mirror planes. 2 of them are marked. There's like 2 more which are going through these tips. And then there's 4 more which are going in between. So we should have 8 mirror planes, and also we should have an 8-fold rotation axis, because you can see that when we rotate this object by 45 degrees, it is indistinguishable from the unrotated case. So that's how we identify an 8-fold rotation axis. And in fact, we have also an inversion center in the center, because when we invert around the center, the object doesn't change. So it's an inversion symmetric object. And maybe as a small exercise, you can try to find the symmetries of this logo. It's the logo of the Technical University of Dresden. So if you recognize here, there should be, I guess, a T and a U for the Technical University. And if you look at it long enough, I'm not sure if some of you see it, there is, of course, one mirror plane, which you, when you kind of flip the logo around this plane, you will end up with the same thing. Then there are more elaborate kind of combination of rotations and inversion, which also should leave it unchanged, but I leave that for those interested to find how that works. Of course, why are we interested in symmetries? Symmetries are always determining properties of objects, and I think from chemistry you might know that, I mean, there are chiral objects which you can actually only by a mirror operation kind of superimpose on each other, like our hands. And these 2 terpenoids, which are carbone, there are 2 types of those, the ones with the left-handed chirality or the right-handed one, and they have very different properties. They smell like completely different things, like one smells like mint and the other one like these caraway seeds. Yeah? So you see that the kind of the symmetry of objects is very important, because it determines its properties. And we try to understand the properties of crystals, specifically magnetic crystals. So we need to identify symmetries of crystals. So crystals are just periodically arranged kind of atoms in space, typically 3-dimensional, but for the purpose of the talk, I restrict it to the plane of the slide here. And now we have sort of these black atoms which are periodically spaced, and to understand the symmetry of this, we don't need to understand the symmetry of all of it. It's enough to basically understand the symmetries of the building block of the crystal. So what is the building block? The building block of the crystal is one sort of unit which, when we sort of translate it in space, can kind of fill all the explain all the crystal points. In this case, this is just this simple parallelogram. Okay. And once we identify this building block, now we need to understand what symmetry operations are valid for this building block. And I'm not sure if I found all of them, but there should be these 2 mirror planes at least, and there should be several 2-fold rotation axes, and the sort of empty space here indicates that there is also always an inversion center connected with these rotation symmetries. So we have mirror planes, inversion centers, rotations, and of course now when we want to have the full symmetry of the crystal, we also should look into these translations. But for the purpose of today, we will ignore the translations, because in fact we are interested in the point group symmetry for those of you who know what I'm speaking about. But basically it's enough to look at the rotations, inversion centers and mirror planes for the purpose of what we want to understand today. Now, as I said before, symmetry determines properties of materials, and what sort of nicely summarizes this is this Neumann's principle. And Neumann's principle states, as it's nicely written here, if a crystal is invariant to a certain symmetry element, any of its physical properties must also be invariant with respect to the same symmetry elements. And that means now we can use the symmetries we identified for this unit cell of the crystal to understand how sort of its properties, the properties of the material, are changing. As an example, I want to give the resistance or resistivity of a cubic material. So here you have a cube, and some of its symmetry operations. A cube has always like 4-fold rotation axis, 4 3-fold rotation axis, several 2-fold rotation axis, and different types of mirror planes. these kind of symmetry operations together with the sort of defining equation for the resistivity. This is basically like Ohm's law, voltage is equal to resistance times current, but the physicists write it somewhat a bit differently. We typically write it as electric field is given as a matrix operation between the resistivity tensor or matrix and the current density. So we just normalize it by space and put some indices and pretend to be clever, let's say. But now we can understand the symmetry of this matrix by just applying the symmetry operations of the crystal. And it turns out that for the cubic symmetries, we end up by only one parameter, which is the resistivity of this cubic material. And now it doesn't matter in which direction of the cube you measure the resistivity of the material, you always must get the same value. So it doesn't matter if you measure along the diagonal or along the edge here, you must get the same thing. Symmetry dictates that it has to be the same. So symmetry is something very powerful. We can really make very hard statements about the properties of matter. Now, unfortunately, this is not where it ends. So we will speak about magnetic materials, and in magnetic sort of magnetization and other properties, they are unfortunately not transforming like you would transform normal vectors. In fact, we call them pseudo-vectors. And what is a pseudo-vector? A pseudo-vector is always something like the result of a cross product. So for example, angular momentum, you should have learned in basic class of mechanics. Angular momentum is the cross product of a real space vector R and the linear momentum P. Yeah? And now, to illustrate what I mean, how these pseudo-vectors sort of translate, convert very weirdly, I want to show you this picture. I mean, I try to give some references to the pictures where they come from. It's a police car basically which is driving away from you. Yeah? Now let's try to figure out what is the angular momentum of the wheels. So the axis of the wheels is here, yeah? And the upper part of the wheels is moving away from us. The real space vector from the axis is upwards. The movement, the momentum is away from us. This means that this red arrow, they kind of show the angular momentum of these wheels. And now comes the weird part. Now we try to mirror this police car. So we introduce a mirror plane here. We mirror the car, but on the other side of the mirror plane, the car is still moving away from us. So actually the same angular momentum of the wheels is true, which means that now the mirror operation of this angular momentum is actually the same. So it doesn't behave like a normal vector. A normal vector, it would just kind of change its direction, right, in a mirror operation. These pseudo-vectors, they don't. So they are actually very special. And magnetization and spin, this property of the electron, this behaves exactly like such a pseudo-vector. Magnetic field is another of those things which behaves like a pseudo-vector, but I would like to come to the spin and magnetization. So here's a sort of summary how this spin behaves upon a mirror operation. So imagine this thing in the middle here, this is the mirror plane. And now you see that when the spin is sort of parallel to this mirror plane, then it just flips its orientation, and if it's perpendicular to the mirror plane, it stays the same. So this is a very special property which you have to know, sort of to understand how this symmetry operations work for magnetization, which behaves like a pseudo-vector. And another of these sort of special operations of symmetry in magnetic, especially in magnetic materials, is time reversal symmetry. Time reversal symmetry means we take a transformation where we change sort of forward moving time to backwards moving time. So everything which moves one way will move the other way when we apply time reversal symmetry. And again, this has impact on magnetic field, for example. Magnetic field, for example, you can produce by current in a loop. Yeah? So when the electrons move that way, for example, you produce this field. When we apply time reversal symmetry, the electrons will move the other way, and the magnetic field under time reversal symmetry changes its sign. So we say it's a time reversal odd property magnetic field. And the same is with the spin. Basically, we go from the red one with time reversal symmetry, we go to the blue one. And you will see then that we need this again to understand the symmetry properties of these kind of magnetic materials, which is what I try to ultimately introduce to you. So the last thing before we get to the sort of, let's say, real scientific slides, I want to introduce to you magnetic materials and band structure of materials. But as far as I understand, you're organic chemists, so you know about bands in your organic materials, and this is something very similar. We just plotted it maybe in a slightly different fashion. So when you think about magnets, I assume a lot of you are thinking of things like that. So you have some north, some south pole, some magnetic field lines, which you can visualize, of course, when you drop some sort of iron filings on a magnet, or these kind of fridge magnets which you use to pin some paper to the wall. The hard disks, these are also magnetic materials. Of course, let's say, I think some of the things which we in our field typically forget, but the largest sort of application for magnets is, of course, in motors, wind turbines. These are literally tons of applications for magnets. Speakers, in the hospital, you have this magnetic resonance imaging, which of course uses also magnets. But the question is, what are we forgetting? Anyone more ideas? There's actually a full class of magnets we are forgetting, at least one. And kind of in the end of 40s, Louis Nail taught us that there is actually more than these. All what I've shown you before, these are ferromagnets. And ferromagnets are those kind of materials where all the moments, all the spins in the material, they align in one direction. So let's see here, we have only blue ones, only up. But Nail found that there's actually two solutions for this interaction of spins on a lattice. It turns out that you can also have this case, where you have half of them blue, half of them red, so half of them up, half of them down. And they have very different properties, but like Louis Nail got for the discovery of those the Nobel Prize, but he said, like, you know, they're interesting but useless. I think he was wrong, but it still sort of remains to be proven in a real application. Currently, they are really only taking support roles. I mean, all what I've shown you on the previous slides, and there's for sure many more examples, it's basically ferromagnets. But ferromagnets have also a lot of sort of not so ideal properties for applications. We have already mentioned the stray fields. The stray fields means that these kind of ordered moments, they produce a magnetic field. We can visualize it by the iron filings, remember. And that is actually a problem in the magnetic storage media, because it means that when we put the memory cells very close together, that the magnetic field of one of them, it tries to interact with the next one. So it is more difficult for us to write a random information. It will try to talk to each other and influence each other. So that's what we don't want. These antiferromagnets, they don't have that. Another thing, we said that, yeah, I mean, the speed of gigahertz is where we are currently with our electronics, but we like to go faster. The intrinsic sort of dynamics speed of antiferromagnets is 1,000 times faster on average. Yeah? So it's this terahertz range, exactly where we want to be. Then this sensitivity to an external magnetic field, this can be an advantage or a disadvantage. This is of course meaning that we can have a very easy way to manipulate our ferromagnet. This is also used in applications by an electric magnetic field. However, in the antiferromagnets, this is something which we don't have, which makes them very robust. This means like it will be much more difficult to sort of delete your information once it's stored, if you manage to do it in an antiferromagnet. But you also have to maybe find different ways to write it. I will give you some hints on what people did to circumvent that. And also, I mean, there are somewhat more materials, and this definitely more different types of materials available for the antiferromagnets than for the ferromagnets. But it remains simply still to be that found the technical application where they really supersede the ferromagnets. I will also explain you why currently there are likely no applications of these antiferromagnets and how we think we found a solution around all this. Yeah. So the applications are currently definitely the biggest plus of the ferromagnets. There are, I didn't kind of go into the details, there are always some antiferromagnets which play sort of a supporting role in all these sort of microelectronics applications, but it's never the active part of the device. So, and that is actually was never the active part of the device because people didn't know how to manipulate the antiferromagnets. They are very robust, yeah, and they also didn't know how to actually read out how the state of the antiferromagnet is. But in the last sort of, let's say, 15, 20 years, there was a lot of research done in this field, and people figured out how to, in the first step, with the help of a ferromagnet, read sort of the state of the antiferromagnet. So they could actually determine from the relative orientation of the ferromagnet and the antiferromagnet below, again with this resistance in a sort of tunnel junction, exactly like the hard disk read head device, what the state of the antiferromagnet is. And And just last year, people found that this can be done also fully with an antiferromagnet. So they had some antiferromagnet, some complicated one on the top, a barrier, and another one of these antiferromagnets, and they could also have these two resistance states which show the relative alignment of the two. So exactly like in the hard discrete head. But so people progressed quite a lot to read these things out, at least in the lab. And also the writing is something people figured out like some 7-8 years ago, how it's done. I was actually at the group in Prague where I'm now working. They figured out that, again, by a special symmetry, and I don't want to go into detail of this kind of these particularities of the symmetry, but again, symmetry helped them to understand which kind of systems you need. When you then send an electric current, you can actually also manipulate the magnetic order. So they managed to, by just sending a charge current, so with no fancy spin polarization yet, they managed to move the antiferromagnetic order from horizontal to vertical, and it again changed the resistance. And you see, it was enough to get a nice publication, but the signals are really small. We speak about milliohms, so this is nothing which you make a sort of industrial application with. But people are thinking about applications already, so they are thinking that we could go towards sort of brain-inspired computing, neuromorphic computing, where you want to have, again, more like sort of analog variation, so not this digital 0 and 1, but you want to have being able to produce various states in between a minimum and a maximum, much more inspired by nature. And they could find this, but again, only in the lab. They also have proven, this was again done in Prague, that by sort of, they could show that the speed of this antiferromagnet is not just something I write down on the slide, but they could really use a terahertz optical pulse to manipulate the magnetic order. So these antiferromagnets, they can be nice, but what is the problem is that it remains on this milliohm level, so it's not enough for industrial applications, and that's what sort of Neil meant with they are interesting but useless. So the problem is that we have, even though we can have some sort of signals from them which are interesting for us, they are always weak. And now the question is, how can we get around that? And that's basically where I want to aim at. And the last ingredient you have to understand for that is sort of how to read these electronic band structure maps. So what is electronic band structure? You know that when we start from sort of distant atoms, we have these atomic levels, the different orbitals which are filled in the atoms, and when we bring many of them close together, which is exactly what we do in a crystal, then due to Pauli exclusion principle, they cannot occupy the same state as when they are separate, so they split up into these bands, and there are different ways to show that. You know that when we have overlapping bands at the energy level where there's the change between the occupied and the unoccupied ones, and you have a metallic system conducting, or we go to something which is slightly split, which we call semiconductor, or something isolating. This is very much the same like you have for sure many systems in organic chemistry which mimic one of these states. In physics, typically we look at this a bit different. We look at it in this kind of what I call spaghetti diagrams, because people sort of plot not just the band, but they also plot sort of the dispersion of the bands, which means they look at the momentum of the electrons, and the momentum of the electrons now, this is this kind of weird axis here with the letters in the bottom, it can be oriented in different directions in the crystal. So you see, and then you need these kind of special kind of graphs which tell you what the x point is, and the x point goes from gamma to x, is the x direction. So then you need to see that here we have gamma, or gamma to x, this would be this dispersion. So electrons moving in this direction, they need to follow some of the energies in these bands in this direction. But in reality, this is nothing else than this thing, just a bit more detailed, because we also resolve this momentum direction. But you could imagine that this here is one band, and here is another one, and the Fermi level is here, so this means this case would be a metal, in fact it is bismuth. Yeah. So we will look at some more of these diagrams, and that's why I show that. So now I would like really to come to kind of our recent results. And it was actually a very clever PhD student in Prague and Mainz who figured that out, a Czech student, Libor Smekal, and he found that there is actually, in addition to these two classes of magnets which I have shown you before, there's another one, which was missed so far. Yeah? And he kind of names them alpha magnets. It remains to be seen if that's something which, like, maybe your kids will learn then in university or school already, but that is at least the idea of LIBOR, that at some point your kids will learn, okay, there's antiferromagnets, there's ferromagnets, and there's altermagnets. Let's see if that works out. But why are we interested in these altermagnets, and especially for spintronics? So I would like to sort of now repeat the classification of these magnetic materials as we nowadays would propose it. Of course, there are still the ferromagnets. But before, maybe let me say, how did LIBOR actually figure out that there are these three classes? He used exactly this symmetry analysis. So he went and he not just looked at one type of symmetry, but he looked at all different combinations, and he figured out that there is in fact not two, but three classes of these magnets. One of them the ferromagnets, antiferromagnets, altermagnets. And now I will tell you sort of what are the different symmetry properties of these three different classes. So in the ferromagnets, we said already before, we have all of the atoms blue, so that the magnetization spin points in the same direction. This means we have, from outside seen, we have a net magnetization. That's one of the criteria of this system. And one can, of course, rephrase that also in terms of symmetry. The most important property is sort of this breaking of time reversal symmetry in the band structure. What does this mean? This means that when I apply time reversal symmetry, and remember I said this means we go from blue to red. We don't have the same object. In this case, it's very clear. We have now a fully blue one. If it's fully red, there's no way that it's the same, right? That means that also all the properties of this crystal, they don't have to obey time reversal symmetry. And in the band structure, this means now if we have these sort of energy levels of the electrons for spin up, and the energy level of the spin down ones, they don't have to be the same. Symmetry doesn't say they have to be the same, so they can be different. Now it's only a question of the microscopic mechanisms, how much they're different, but they can be different. And very typically, this is how it would look for a ferromagnetic material, these band structure diagrams. Of course, simplified, we have here this momentum vector, and here the energy, and typically we would have two bands split sort of isotropically in all the space between the spin up and spin down. And that's also why these materials are so sort of favorable for the spintronics applications, and all of the current applications are based on those, because we see these blue and red lines. So clearly when we now send a current, for example, with an energy here, it has to be on the red state, so it has to be spin polarized. On the other hand, there are these antiferromagnets. So antiferromagnets are magnetically compensated. So this is basically exactly like nails, so to envision them. We have magnetic compensation, so this means we have half of them blue, half of them red. This means we have no net magnetization, is already different from here. But now we have also no time reversal symmetry breaking in the band structure. And how do you see that? Actually now, let's apply time reversal symmetry to this object. And you see this means basically we go from blue to red. So we see every blue one is a red one, every red one is a blue one. I repeated the crystal sort of left and right ones for you, so that you can better see what I will do next. Next I will just translate the crystal by one unit cell. And of course one unit cell translation is a very boring thing, because it leaves the system typically unchanged. And in this case, after the time reversal symmetry operation, shifting the crystal by one unit cell, it brings us back to the very same picture we had in the beginning. So you see now we have again red on the bottom, blue on the top, as it was in the beginning. So this means that in this system, this time reversal symmetry together with translation is a symmetry property of the crystal. And in the band structure, this means we have no time reversal symmetry breaking. In the band structure, this is something you have to know. The translations, they don't matter, so we can just ignore them. So this means time reversal symmetry is a property of the system. And that means, since time reversal symmetry changes the spin up to spin down, this means now we have to have the same bands for both of these states. And that means it's boring. Or that's why we have problems to actually have spintronics applications for these materials, because spin up and spin down electrons have followed the same states. So we cannot have these spin polarized currents in these systems. And now LIBOR figured out that people actually forgot something when they did this kind of symmetry analysis. And what they forgot is, as trivial as it may sound, they didn't consider all the atoms in the unit cell. So it turns out that if you consider, in addition to these kind of magnetic ones, also the non-magnetic ones, you can find cases where you still have this magnetic compensation. So you still have half of them blue, half of them red, but you sort of still have a different kind of symmetry. And the difference is, now we have still no magnetization, so we have one property from these antiferromagnets, but we have the breaking of the time-reversal symmetry like it was in the case of the ferromagnets. And that means, in general, again, the energy of the spin-up electron is different from the spin-down one. And that means we can again have these blue and red bands. And in fact, the splitting in these systems can be equally strong as it is for the ferromagnets, which means now we can have these spin polarized currents in a system which otherwise has magnetic compensation. This means that the hope is that we can have the terahertz speed together with the favorable properties of the ferromagnets in these materials. And just recently we figured out some sort of experimental confirmation for that. And it was done in this kind of material, which is manganese telluride. And I want to show you sort of how we, at least from symmetry point of view, can understand that this is an altermagnet. So manganese telluride has this kind of crystal structure. It's called nickel arsenide type crystal structure. It's a hexagonal structure. But for the purpose of today, I just draw it in a different way. It's an equivalent representation. I put the kind of manganese atoms, these are these purple ones, into the center of octahedra of the tellurium atoms. And you see I already indicate there's one sort of blue octahedron and one red one, because they will have the opposite spin polarization. That's actually the first thing we had to do. We had to understand the magnetic structure. And in fact, it was reasonably easy, because there's already, let's say, 60 years of research on that material, and so we know reasonably well what the magnetic structure is. And we did some more work on that in the form of thin films a few years ago, and we figured out, okay, the magnetic structure looks like this. So we have half of the manganese atoms with the magnetic moment, they're spin pointing to the right, and half of them to the left. And that's why I draw them red for one case and blue for the other. And now Lebor wrote down exact kind of rules, what symmetry operations you have to fulfill to be an altermagnet. And the sort of boiled down definition, I would say, is that the opposite spin sublattices, this means that the blue and the red lattice, which we had in the previous picture, they have to be connected by a crystallographic rotation transformation, possibly combined with translation or inversion, but not translation or inversion alone. Okay, sorry. So, but how to kind of visually see that? So let's try the pure translation as an example. So pure translation means I move now the, oh sorry, let's do it once more. So let's move the blue up to the red. At the same time we change the color. This means we translate it and we apply time reversal symmetry operation, exactly like we did before for this kind of 2D cartoon. And you see, okay, the magnetic atoms, they overlap, but we have a problem here. We see that the non-magnetic atoms, they're actually not overlying. Yeah? So that we clearly see that this is not a symmetry operation. So this means that we can basically already exclude that we have an antiferromagnet. It's magnetically compensated, but it's not an antiferromagnet. Antiferromagnets must have this symmetry operation. However, now when we do a sort of slightly different operation, such a twisting and pushing operation, called a screw axis, it's exactly what is written here. We have a crystallographic rotation transformation, in this case a 60-degree one, and at the same time we shift the atoms by half a unit cell up. And in addition, we change the color from blue to red. So now we have in fact shown that yes, these two, the blue and the red lattice, they are connected by this rotation-like symmetry operation. So in fact, symmetry tells us this is an altermagnet. So now we just have to kind of find a way to measure it. So Lebor, of course, figured out in more detail how to classify these altermagnets. I don't want to go to details here. I just want to say there are different types. He calls them D, G, and I wave. And this is in analogy to the kind of atomic orbitals. You might remember, like, you know, we have S, P, D, F, G orbitals. And in this analogy, if you take only the even ones, you see even in angular momentum. And of course, we want some which have a finite angular momentum. So the S one is not interesting for us, let's say. But it starts with D. Then it's G, and then if you continue this, you would come to the I. So in our case, this manganese telluride is a G-wave altermagnet. Its band structure looks a bit like this, which is similar to one of the G-wave orbitals in atoms. And now, of course, we can do these band structure calculations. And there is one sort of detail, but of course important detail, which I kind of hid from you. all this, what I told you, is exactly true only in a limit of when we ignore sort of that the spin actually interacts with its environment. This means we say we don't have spin-orbit coupling. In the case we don't have spin-orbit coupling, all of what I said before is exactly true, and spin-orbit coupling is a small correction to what I've said before. So, but if we now do these calculations without this interaction, then we get exactly sort of what symmetry tells us. Symmetry told us there are some certain planes where we still have sort of degeneracy in this system, and those are those where we get that the spin up and the spin down, they have the same dispersion. So that's sort of the boring plane. But if we go into a different part of this Brillouin zone, of this space, and calculate the dispersion, then we get these nicely and widely split kind of fully spin polarized bands. And then of course in real life we cannot turn off this, this interaction of the spin and its environment, so we have to do these calculations with this effect considered. And when we do that, you see then it's getting a bit more complicated, but in the end, in this picture, the main picture stays the same. It's a small correction. Here in the case where there was nothing before, and it turns out that there is also some finite effect coming, so it's even getting, let's say, more interesting. But what we now aim to do is actually to measure dispersions like this. Okay, how do we do that? We need materials. So these materials, we grow them by molecular beam epitaxy. This means we provide a single crystalline template, a substrate, and we shoot on the atoms sort of in the right stoichiometry, and we provide a bit of a heating so that there's enough energy for the crystal to grow properly. But you might understand more of that than me actually. So we are just like kind of stupid physicists shooting the stuff on it, and it somehow turns out to work. And in addition, we also have these single crystal grows where we kind of just weigh the compound, the elements together. We melt it, we let it cool down slowly, and it also crystallizes. And then it turns out we just check its properties. We check that the magnetic properties are like they were previously sort of found. I think we don't need to go to the detail here. We do the diffraction to see the symmetry. We said it is a hexagonal material, so we see the six-fold symmetry here. We do also the transmission electron microscopy, where we directly see the columns of the atoms, and everything fits to the picture which we had before. There are some manganese atoms which should be magnetically ordered, and the tellurium in between. And then we need this sort of fancy experimental equipment which actually allows us to measure these band dispersions. That's called ARPAS, angle result photoemission spectroscopy. This means we shoot on photons, in this case very intense photons with specific wavelengths, and they are produced by a synchrotron facility. Who has an idea what a synchrotron facility is? So a synchrotron facility is actually like a large storage ring. So we like CERN, but for a different purpose. So you use charged particles which you accelerate to 99.999 something percent of the speed of light, and you accelerate them in a large ring. And because you have an accelerated charge, you produce actually radiation. That's synchrotron light. And this synchrotron light is a very powerful tool in condensed matter research, because it can give kind of a light in a very large wavelength range. And what we need here is something like ultraviolet light to X-ray light to investigate these materials. So this light comes from these large rings. These rings are typically like hundreds of meters in diameter. And then it comes to one of these pipes here. It's already sort of a bit preconditions, and then it goes into in one of these chambers is your sample. The photon hits your sample, and it excites some electrons. Those are coming out, and you analyze their energy and their direction, and from that you can sort of calculate back to the dispersion of the system. So that's one of the pictures you get. You see again the hexagonal symmetry, but this is for one energy. Now we look here only at two dispersion directions, kx, ky. So what we are interested in is to look at kx versus energy, for example. And that's what we do here. We have here a map of kx versus energy, and you see here we see these bands, and this is sort of looks quite similar to when you then, I mean, this is how it's measured, let's say. And this is after a bit of what I call massaging of data, which you have to be nowadays very good at to sort of visualize exactly what is there to be seen. So these data are a bit filtered compared to this raw data, and you actually can see that there are these bands, and this corresponds very nicely to these calculations which the theoreticians do. And these tell us that indeed we found that there is this splitting of these two kind of types of the spin polarizations of the electrons. So we have an upper branch, which is the red one, spin up, for example, and we have the spin down branch, which is the bottom one. So then, of course, we had to do many more control experiments to sort of prove that this is really true. For example, we had to study the temperature dependence. So all of this, what I told you, relies on the magnetic order. So when the magnetic order is gone, so when you heat the material above its transition temperature, then also the splitting must vanish. So we tracked the splitting, how it evolves with temperature, and vanishes exactly, or more or less exactly where the Nell temperature of the material is from other measurements. And I think I'm gonna kind of jump over this part of the talk. More symmetries, more properties of the system which follow it, these symmetries. In particular, also some transport properties. We try to now exploit the kind of, we try to really get towards the direction of using this these spin polarized bands for electronic properties, but we are not quite there. So we are just 2 weeks ago, we had the experimental confirmation of that these materials are indeed belonging to this category. Now we try to kind of push it to applications. Let me go over this. But in principle, we can summarize that there are these kind of now different resistance states in zero field, which allow us basically to distinguish two states which were previously thought to be the same. So this is kind of, you know, bottom manganese to the right, next one left. This is bottom one left, next one right. People thought that these states are exactly the same, but now it turns out actually you can have different resistance, you can have different kind of spin polarization properties of the current for these states, and that's what we will try to exploit. Everything obeys the symmetry. There are more than just one material. This was just one example. We already identified experimentally 3 of them. In theory, like several hundreds of them were found to be available. So we really think that, or we hope that this is the next big thing in sort of electronics, because we can really kind of now get spin polarized currents in otherwise compensated magnetic systems, which should allow us to be 1,000 times faster than existing technology. And we hope that that sort of will help us to kind of provide devices with lower energy consumption for future electronics. So I would like to thank you for listening, not falling asleep. Thank you.
Thank you. And now if you have any questions.
Thanks for your presentation. Maybe from theoretical chemistry perspective, how useful can DFT models or chemical quantum calculations be useful for your applications, and how much precise are they if you use them? Thanks.
So they're super useful. I'm not sure if for applications, but for our research, definitely, right? Because, I mean, it started all by doing the symmetry analysis, but somehow people started to believe it, I think, once they calculated it by DFT. And all the calculations of these band structure diagrams I showed you, this was all DFT, and without that, I think it would not be possible. How accurate are they? This depends. You saw in sort of this specific zoomed kind of version of it, it was fitting very well. And of course there are some tuning parameters. You might know there is Hubbard U or so, and you can sort of tune a bit to get to this. But in fact for this minus terabyte, it turned out that it worked very well without a lot of tuning. But it's the first and only material where we have this kind of agreement between the calculation and the theory. For the others, the problem is often also that the measurement quality is much lower, and then the problem is that you can dream of the agreement, but I can also not say it disagrees, right, because you don't see enough features. I guess you know what I'm speaking about. But generally, I think it's a very useful tool for us, absolutely essential actually. But of course, one has to always treat it with a grain of salt and know how to look at it.
Any other question? I would have one. So you've shown that basically in order the symmetry you see in altermagnet, just one so far, was basically a screw. screw, that you are basically screwing the symmetry and moving a little bit further. Would it be possible something else as well for this organization, or will all of them look like screws?
No, they won't. It really is, this is super individual, like what operation it is which links these two sublattices. In this case, it's actually, that's why I also show it in 2D. You can imagine rotating, just rotating it is by 90 degrees, changing the color, you are back at the original picture. So in this case, it's a normal rotation axis. The only statement which is made sort of it, that it cannot be that you have between these two, between these two, you cannot have an inversion symmetry. That's also one of the reasons why this was missed so long. I mean, this is not that people are stupid, but somehow in these magnetic symmetries, the people, they typically blank out these non-magnetic atoms. And now if you remove here the black dots, yeah, then all this interesting physics are gone. And there's one more twist which I was again hiding, let's say. People classified this by the common sort of magnetic symmetries. Magnetic symmetries means they link the symmetry operation of the crystal space, of the real space, with the one of the magnetization. This means when I turn one of it, I turn also the other. And now what I just told you with the fourfold rotation here actually fails, because a fourfold rotation, which means 90 degrees, it doesn't turn around the moment, but it only turns it by 90 degrees. So to identify that, Libor had to go back, but the mathematical models were all existing from Russian literature, let's say. The models which decoupled this spin space and the real space. And that was the key thing to use, which allows you now to have a symmetry operation in the real space, only affecting the real space, not the magnetization, and symmetry operations which only affect the magnetization without changing the real space. And once he kind of could decouple these two spaces and use this kind of mathematical concept, let's say, then it's not sort of by chance that he gets three categories. It's really symmetry tells you there are these three categories. They are completely distinct, and so it's in fact a very sort of, I mean, symmetry is precise, right? So in this limit, which is no spin orbit coupling, you get for these collinear magnets exactly these three categories. Period.
Any other question? Maybe I would have another one, because now you are speaking about the symmetries, there were DFT as well, and the let's say current joy for theoreticians is AI and machine learning models. Would it something like that be possible by training some to generate the possible models and possible compositions by the AI?
Absolutely, people tried. But let's say it revealed one of the weaknesses of AI, which is the user. and the people, so there is papers which say, you know, we discover by AI one more alpha magnet. But the problem is that they didn't understand the symmetries. So they fed the AI system with some rubbish, so rubbish in, rubbish out. Mm-hmm. So yes, it's possible, but I think that the people need to be more clever to actually sort of use it right. That's one thing. And also, since symmetry is precise, actually, it's so once you know the magnetic kind of arrangement in your crystal, you don't need AI to say what it is. To find the next one, which is not yet known, one could try to use AI, but I think then it's getting really very tricky, because you have to trust the DFT sort of ultimately. And especially when it comes to predicting kind of which kind of magnetic order you have in a crystal, that's a very tricky business. So I mean, the energy differences sometimes between different types of magnetic order in these systems is very small, and I mean, I'm not sure if I have a good picture somewhere. I have, but for example here, one example for one of these compounds which we identified to be ultramagnetic, people published this magnetic structure. We think it's this one, and the difference is very subtle. It's just that here you have this blue, red, blue, red, blue, and here you have red, blue, blue, red. And I think that by sort of energy calculations, it's very difficult to distinguish these two. But the symmetry properties, once you have the sort of boring antiferromagnet and once it's an altermagnet. So I think you have to, you need to be very precise and trust the tool. And there I'm not sure if DFT is sort of good enough to really, so it will give you a result, but it might not be correct. Yeah.
So, any other question? If not, then thank you again. And uvidíme se ve čtvrtek 21.3. A to bude stírat červinka. Takže teďka máte skoro celý měsíc, kdy budete mít více času. A pak to teda bude ve čtvrtek. Místnost ještě upřesním, myslím si, že to nebude aula, ale nějakou místnost tam to snad najdeme. Čas bude stejný, čas bude 13:15. Protože je ideální na to, aby lidé stíhali přijíždět z jiných měst. Tak jo, tak přeji hezký zbytek dne a hezký den.